This is a Chapter 26 class example problem. I did this in class, but if you're absent or if I went too fast, which I did go pretty fast, you might want to watch this video. So anyway, what we have is we have some students that did a study, and they were looking at eye color, and they were looking at what hand your dominant hand is. Is it left or right-handed? And they want to see if there's a relationship between the two. So one of the things that we notice quickly is that we have counted data for, I think, two categorical variables. Okay, it looks like this is variable 1, eye color, and variable 2 is your hand, your dominant hand. Okay, and then I would say that there's one, they sampled from one population, so there's only one group. Okay, so when that happens, usually what we have is a test of independence. Okay, we see that the data was collected randomly, so they used a random survey. Okay, so it looks like we're in pretty good shape. When we do the hypotheses, we always want to do it's going to be the same, and then not the same. That's sort of like, just think that first and then think about what you want to write. So here we want to say, well, if they're the same, we want to say that handedness and eye color are not associated. In other words, they're independent. Okay, they're not associated. We would expect the proportions of brown, blue, green, and other to be the same for those people with left hand and people with the right handed. Okay, so if not the same, we kind of just reword it with a slight change. Handedness and eye color are associated. Okay, now be careful to use the word correlation. Since we have categorical variables, we're just going to talk about association. Remember that when we have scatter plots, we have two categorical variables, and then once we know the conditions are met, we could say there's a correlation. But that's when we're working with quantitative data, not categorical, quantitative. Okay, so what we want to do is we want to proceed with a test of independence. If we had two groups of data and one variable, then it would be a test of homogeneity. But here we have two variables in one group, so it's a test of independence. And we're going to use a chi-squared model. And the degrees of freedom, let's see, that's going to be row minus 1 and column minus 1. Okay, but before we get too far ahead of ourselves here, we need to do this expected cell frequency check. Remember that we need each cell, the cell counts, all cell counts, to be greater than or equal to 5. Okay, so the way you would check is first you would do second matrix, okay, and you would do edit first and set A to be 4 rows and 2 columns. All right, and then you put the data in, and enter the data. Okay, so after you do that, then you would just do stat. You would do stat test and run the chi-squared test with matrix A as the input and B as the output. Okay, so once you do that, then you need to go back to second matrix, but this time select B. To see, B will have the expected cell count. So here's what you would get. Here's what I get. Okay, the expected values in B, I get 6.7, 5.2, 4.4, 2.5, 3, 5.5 to 7.7, 23.5, and finally 13.4. Okay, so the problem is that we don't meet the criteria right here. 4 and 2 are too small. Now, sometimes that means you just can't do the test. If you're doing a project, you're going to have to go out and collect more data. If you get more data, maybe these expected values will go up. So here, though, we can kind of see that green and other could be combined. Okay, so what we can do is we can add 2 to 4 and get 6. Okay, and we can add 21 to 12 and have 33. Okay, now you have to go back to second matrix and now change the 4 to a 3, and then you have to change the last row. You have to put in a 6 and a 33. Then redo the test. Just run calculate. Then go back and look at matrix B for the expected values. And here's what I get. I get 7. So I'm going to put them in here. 7, 5.5, which is good, and 6.5. Okay, so we've fixed the problem. And then just for completeness, 35.3, 27.7, no, 0.5, and 32.5. 32.5. Okay, so now after changing the data to 3 rows, all cell counts expected cell counts are greater than or equal to 5. Okay, so that took a while, but that's important. Otherwise, it's not appropriate to proceed. So now the conditions are met. So we will proceed with a test of independence. Again, we have 2 variables in one group. So that's what we're going to do, test of independence. Okay, so now you probably already did this, but if you do second, now I keep messing up. It's not second. To do the test, we want to do stat test and do chi-squared test. And this time you want to do draw. And you get everything that you need. Okay? So first we see that the chi-square value is 0.7085. and the p-value, which is the probability that the chi-squared value is greater than 0.7085. Let's see, that's 0.7017. Now you could do this manually if you wanted. You could do chi CDF, and you could put in 0.0785 to 999. And oh, we didn't finish the degrees of freedom. This is 3 minus 1 and 2 minus 1, so that's just going to be 2 times 1 is 2. So we would put in a 2, and we get the same thing. Don't have to do that. This part is fine. Okay, so one thing you do need to do, though, is observed minus expected squared divided by expected. Now, if you label your expected values, if you go up here and just say observed values, and sort of do expected values like that, you probably are okay with this arrangement, just saying this equals this over here, the value. To be safe, and if it doesn't take long, and you do need to know how to do this, 7, right, squared divided by 7, you need to know how to sort of 36 minus 35 squared divided by 35. So it's always the observed. So 7 minus 5.5 squared divided by 5.5. And then 26 minus 27.5. That one's going to be negative 27.5. And finally, 6 minus 6.5 squared divided by 6.5. And then 33 minus 32.5. Notice our numbers are pretty close now. That's why we have such a high p-value. So we evaluate p the same way. So for the picture, you will see on your calculator that we have 0, and then it's not going to have a hump to the curve yet. Alright, so, but we're not that far away. The chi-squared value is 0.708, so it's not even 1 unit away. Okay, so the p-value is quite large. Alright, so the p-value is large, so we fail to reject HO. There is insufficient evidence that handedness and eye color are associated. Now, let's see if there's more context to this. Okay, you could say among students at Washington High School, to really get deeper towards the question and make sure that you've narrowed. What you don't want to do is make some kind of conclusion for all students, because we really only measured a population of high school students from this school. Okay, so again, the keys here to this problem were recognizing that you had 2 variables in one group and in recognizing that the expected cell frequency was not met and noticing how to fix that. Okay, so good luck with this.